This presentation is delivered by the Stanford Center for Professional Development.
Hey, I guess we've started. Well, we get the video-induced drop-off in attendance. So my first announcement is this afternoon at 12:50. That's not this afternoon. Whatever. I guess technically it is. Later today at 12:50, believe it or not, we're going to make history by having an actual tape behind. So where we're going to go back and do a dramatic reenactment of the events that occurred on the first lecture. That's so I don't know, so people on the web can see it or something like that. So that's 12:50 today. It's here. Obviously, not all of you are going to come, but those who do come will get a gold star and extra help with their projects, or who knows what. We'll figure something out. So please come, because although it's never happened to me in a tape ahead or tape behind, you know it's every professor's worst nightmare to go to a tape ahead and have no one there. So, in fact, it's not even clear. There's some philosophical questions, like could you, and just practical ones, like could you actually give a lecture if there was no one there? I'm pretty sure the answer is no. But okay, so we'll start in on continuing on the constrained subgradient method, projected subgradient method. Sorry, let me make one more announcement. Homework 1 is due today, which has a couple things on it. We've pipelined, so homework 2 is currently in process. And then we're going to put out a homework 3 later tonight, something like that. So, hey, listen, it's harder to make those problems up than it is to do them. Come on. We can switch. You want to make up the problems and I'll do them? We can do that if you want. It's fine with me. I can do well, of course, your problems have to be well posed, and they actually have to kind of mostly be correct and kind of work. So anyway, we can switch if you want. Just let me know. Okay. So let's look at projected subgradient. So the projected subgradient method, let me just remind you what it is. It's really quite stupid. Here it is. It's amazing. Goes like this. You call f.get subgrad, get here at x, to get a subgradient. So that's you need a weak subgradient calculus method implemented. So you get a subgradient of f. You then take a step in the negative subgradient direction with a traditional step size. Of course, this in no way takes into account the constraint, and then you project onto the constraint. Now this is going to be useful, most useful, when this projected subgradient method is going to be most useful when this projection is easy to implement. And we talked about that last time. There are several cases where projections are easy. That's it. Projection on the unit simplex. That was it. Homework 3. Coming up. Okay. Projection on unit simplex. Okay. So obvious cases are projection on the non-negative orthant, projection onto the cone of positive semi-definite matrices, but you'd be surprised, there's probably about 15, 20 sets that it's easy to project onto, or easy in some sense. Of course, you can also project onto other sets, like, for example, polyhedra or something like that, but that would involve using quadratic programming or something like that. Okay, so this is projected subgradient method, and a big use of it is applied to the dual problem. Now this is really a glimpse at a topic we're going to do later. So later in the class we're going to look at this idea of distributed, decentralized optimization. So far kind of everything we've been talking about is centralized. You know, you collect all the data in one place and calculate gradients and all this kind of stuff. In fact, we're going to see beautiful decentralized methods, and they're going to be based on this. So this is a glimpse into the future. Maybe not even too far a future, maybe like a couple of lectures or something. But let's see. Okay, so we have a primal problem, minimize f0 subject to fi less than 0, and we form this dual problem, which is maximize the dual function at lambda. These are the Lagrange multipliers lambda. These have to be non-negative because these are inequality constraints like this. And the projected subgradient method is very easy because we're maximizing this concave function subject to the constraint that you're in the non-negative ortho. Projection on the non-negative ortho is completely trivial. You just take the plus of the vector component by component. So the update's going to look like this. You will find a subgradient of minus g here. So we'll find a subgradient of minus g, and then we will step in the negative subgradient direction. Actually, I suspect this is correct, but this could be a plus here. I don't know. And the rule is for 300 level classes, I don't even care. If it's a plus, then you fix it or something like that. I think this is right. It's confusing because that's a subgradient of minus g. So, okay. So you take a subgradient step in the appropriate direction. So I'm allowed to say that in a 300 level class. And then you project here. So that's it. Now, by the way, I should mention, again, kind of going towards, if I solve this dual, when is it that I can actually extract the solution of the primal problem? Just, again, this is 364A material, which we covered way too fast, but I don't know. Does anyone remember this? What is it?
It's very feasible.
Sure, we're going to need strong duality holds. If it were strictly feasible, you'd have Slater's condition and strong duality would hold. That gives you zero duality gap, and I guess if you don't have that, then you can't solve this at all because the optimal values aren't even the same. So let's assume that there's more actually to it than just that. The sledgehammer condition is this. What you'll need is that when you find lambda star, what you want is that the Lagrangian at lambda star should have a unique minimizer in X. If it does, then that X is actually X star up here. Okay? So that's the condition. A simple condition for that, you should go back and read this because we're gonna be doing this in a couple of weeks, and actually these things are really gonna matter. So we're gonna do network flow methods and all sorts of other stuff, and they're actually gonna matter. Here's one sledgehammer condition is F0 here is strictly convex. Because if F0 is strictly convex, then F0 plus some lambda I Fi, where Fi are convex, is also strictly convex. For any lambda, including all lambda 0, it doesn't matter. It's strictly convex. If it's strictly convex, it has a unique minimizer. So just to go back to this, you would actually calculate the optimal lambda star. You would then go back and get the minimizer, the Lagrangian with respect over X, call that X star, and that will actually be the optimum of this problem. Okay. So let's work out the subgradient of the negative dual function. So it's actually quite cool. Let's let X star of lambda be this. It's argmin of the Lagrangian. So this is just exactly what we're just talking about. And here's your sort of the big sledgehammer assumption is F0 is strictly convex. So by the way, in this case, you might say, a lot of times some of these things are silly. They're sort of things that basically only a theorist would worry about. I mean, somebody should worry about them, but they have no implications in practice. And I'm very sorry to report that this is not one of those. There are many cases in practice with real methods where this issue comes up. It's real. It means that methods will or will not converge, and you have to take extra effort and things like that. So, okay. All right, so we'll just make this sledgehammer assumption here, the crude assumption. F0 is strictly convex. That means this is strictly convex here, and therefore it has a unique minimizer. And we're going to call that minimizer X star of lambda. It's a function of lambda. Okay? So that's X star of lambda. And, of course, if X star is the minimizer, then G of lambda is F0 of X star of lambda plus lambda 1 times this. It's the Lagrangian evaluated lambda star. Okay, so a subgradient of minus G at lambda is then given by this. It's HI is minus Fi of X star of lambda. Now, this is actually quite an interesting, first of all, let me explain that. G, let me see if I can get this right. G is the infimum over z. It's the infimum over z of this Lagrangian here. That's the infimum of. That's what g of lambda is. So negative g of lambda is a supremum. How do you calculate a subgradient of a supremum? No problem. You pick a point that one of the points that maximizes. In this case, there's a unique one. That's what this assumption says here. So you pick the maximizer, that's this, and then you form this thing, and then you ask yourself, what is the gradient, subgradient of this thing with respect to lambda? That's an affine function, and so the subgradient is simply this thing here up to this thing here. And so, again, modulo minus signs, my guess is that this one's correct, but I guess we'll hear if they're not. And we'll silently update it, but I think it's actually right. So a subgradient of minus g is this. By the way, that's a very interesting thing. Let me say what that is. This, if this is positive, then let's see, what does that mean? If hi is maybe we don't have. Well, we can work it out. Sure. Fi of if fi is negative, that means that the ith inequality constraint is satisfied. If it's positive, it means it's violated. So that means that hi, if it's positive, it's something like a slack. So hi is a slack in the ith inequality. If hi is positive, it means the ith inequality is satisfied. If hi is negative, it is violated. And hi is the amount by which it's violated. Okay, so here's the algorithm. Here's the projected subgradient method, just translated using this subgradient. Notice how embarrassingly simple it is. So this is projected subgradient method for the dual. And it basically says this. It says you start with some lambdas. You could start with all lambdas equal to 1. For that matter, start with all lambdas equal to 0. Just start with all lambdas 0. It says at your current lambda, minimize this Lagrangian without any consideration of feasibility for the primal problem. Now, when you minimize this thing here, and basically the lambdas are, of course, prices or costs associated with the constraints, right? So this is sort of a net here because it's sort of your cost plus, and then these are like charges and subsidies for violations. It's a charge if it's a violation, and it is a subsidy if fi is negative, which means that you have slack, and then actually you derive income from it. Okay, so that's what that's the meaning of this. So it says what you do is you set all the. It's a price update algorithm, and you start with any prices you like. They have to be non-negative. You start with the prices. You then calculate the optimal x. No reason to believe this optimal x is feasible. By the way, if the optimal x is feasible, you're done. You're globally optimal. So if fi of x star at any step, if they're all less than or equal to 0, you're done, optimal. And not only that, you have a primal dual pair proving it. Okay, otherwise what you do is you do this. And this is really cool. You go over here, and you look at fi of x. If fi of x, let's say, is plus 1, it means that your current x is violating constraint I. Okay? It says you're violating constraint I. That says the price is not high enough. So it says increase the charge on resource 1. If resource I, if fi represents a resource usage. So it says pop the price up in that case, and alpha tells you how much to pop the price up. In that case, the plus is totally irrelevant because that was non-negative. You added something, you bumped the price up, and there's no way this could ever come into play. Okay? Now, so it says, this is the name, I should say the comment. If you make a little comment symbol over here in the code, you should write on the thing, price update, because that's exactly what this is. The price update. So what you do then is this. If fi is negative, that's interesting. That means you're underutilizing resource I. It's possible that in the final solution, the constraint I is not tight, in which case it doesn't matter. That's fine. That's the right thing to do. But you're underutilizing it. And what this says is, in that case, that's negative. This says drop the price on that resource. It says drop the price. Okay? However, now this comes into play. It says drop the price, but if the new price goes under 0, which messes everything up, because now it encourages you to violate inequalities, not satisfy them, then you just make the price 0. Okay? And so, for example, if the ith inequality is in the end going to be at the optimal point is actually going to be not tight, then what's going to happen is that price is going to go to 0, like that. Because at the iterates, you know, you'll be underutilized here. That'll be negative. That'll be 0 from the last step. This will become negative. The plus part will restore it to 0, and so that's that. Okay, so this algorithm, I mean, it's actually a beautiful algorithm. It goes to the variations on this go back into the 50s and 60s. So, and you find them in economics. So this is it's just a price update, or I think this is one of this would be part of there's a bigger family of things. I guess they call this a tâtonnement process or something like that, where I don't know who's taken economics and knows the name for these things. Is that no one? Too early? Does anyone remember? Come on, somebody here took an economics class and saw some an advanced one and saw some price adjustment methods. Okay, we'll just move on. No problem. Okay. All right. So in that method, it says that the primal iterates are not feasible, right? Actually, if you ever hit an iteration where the primal iterates are feasible, you are now primal dual optimal, quit. You quit with perfect. So what it means is, in a method like this, projected subgradient applied to the base problem, after each step you're feasible because you project it onto the feasible set. So that's a feasible method. And all that's happening is your function value is going down. I might add not monotonically, right? Because these are not descent methods. So, but your function value is coming down to the optimal one, non-monotonically. In a dual subgradient method, what's happening is that primal iterates are not feasible. What happens is these things, you're approaching feasibility. That's what happens. In fact, you'll never hit feasibility. If you hit feasibility, you terminate at the end. And in this case, the dual function values, all of which are lower bound. So the one nice part about this dual subgradient method is at each step you have a global lower bound on the original problem, because you do evaluate g exactly at each step. So you have a lower bound. By the way, there's a couple of tricks. I think these are in the notes. So if you read the notes, this becomes especially cool when you have a way, some special method for taking x tilde and from it constructing, I want to say projection, but it doesn't have to be projection, but constructing a feasible point. Could be by projection. So if you can construct a feasible point, then this algorithm will actually produce at each step two things. A lower bound, a dual feasible point. You'll know g of lambda, that's the lower bound on your problem. It'll go up non-monotonically. And you'll also have a feasible point, call that x tilde of k. Tilde is the operation of constructing a feasible point from xk. And then you get primal points whose function value is going down non-monotonically. Then you actually get a duality gap and all that kind of stuff. So, okay. So I think we talked about all this. That's the interpretation of the thing. It's really quite beautiful. The coolest part about it you haven't seen yet, and the coolest part we're going to see later in the class, not much later, but it's is that this is going to yield decentralized algorithms. So for example, you can do network flow control, you can do all sorts of crazy stuff with this, and it's quite cool. But that's later. Okay, so we'll just do an example just to see how this method works, or that it works, or whatever. Oh, I should mention something here. And you might want to think about when would this algorithm be a good algorithm, or when would it look attractive? And let me show you actually one case just right now immediately. This is trivial calculation. The actual only work is here. And what this means is you have to, at each step, the work is actually in minimizing this Lagrangian. So basically, at each step, there will be prices, and then you minimize the Lagrangian. That's going to be the work. Therefore, any time you have an efficient method for minimizing this function, you are up and running. Okay? So, for example, I can name a couple of things. Suppose you have a control problem, and these are quadratic functions, right? Then if you have if this weighted sum is also going to be one of these convex control problems, it means you can apply your LQR or your Riccati recursion or whatever you want to call it to that. If this is image processing, and somehow this involves something involving, 2D DFTs and all sorts of other stuff, the grad student before you has spent an entire dissertation writing a super fancy, multi-grid blah, blah, blah that solves this thing well. If it solves least squares problems there, and if this is a least squares problem, you're up and running. So, and you wrap another loop around that where you just update weights and then repeatedly solve this problem. So it's good to be on the lookout. Anytime where you see where you know a problem where you have an efficient method for solving, actually just minimizing a weighted sum, this is what you want to do. Okay. All right, let's look at an example. It's going to be just quadratic minimization. It's not a big deal. And we'll make p strictly positive over a unit box. So notice here, we could do all sorts of things with this. We could do the projected subgradient primal is easy here. So projected subgradient primal goes like this. You take x at each step, and then you x minus equals alpha times px minus q. Everybody follow that? That was x minus equals alpha g. And then I take that quantity and I apply saturation, because saturation is how you project onto the unit box. Everybody got that? So that's the that's the method. Okay. So that would be primal subgradient method applied to this. By the way, I should mention something here, and that is, these are not endorsements of these methods, and in fact, these methods only make sense to actually use in very special circumstances, right? If you just want to solve a box-constrained QP like this, and x is only 2,000 dimensions, or who knows, it could be all sorts of other things, you are way better off using all the methods of 364A. So that's just an interior point method, right? So actually, if someone said, "Oh, I'm using primal decomposition or dual decomposition to solve this," I would actually really need to understand why. There are some good reasons. One of them is not, I don't know, just because it's cool or something. I don't know. I mean, that's not. I mean, here, for example, this would be so fast if you made a primal barrier method for it. It would be insane. So there are only special reasons why you'd want to do this. One would be that when you write down this dual subgradient method, it turns out it's decentralized. That would be that works as a compelling argument. But just to remind you, these methods are slow. They might be 2 lines, right, like that. I guess if you put a semicolon here, it's 1 line. They might be 2 lines. They might be simple, but they're not. These are not the recommended. I just want to make that clear. Okay. So here's the Lagrangian, and indeed it is positive. This is positive definite. It's a positive definite quadratic function for each value of lambda, because you don't even need this part. It's positive definite already here. And so here's x star. This is p plus diag of 2 lambda inverse q. And the projected subgradient method for the dual just looks like that. So in fact, it makes perfect sense. It even goes really back to 263. And it goes back to regularization, right? Because if you didn't know anything about convex optimization, but you knew about least squares, that describes a lot of people, by the way, who do stuff. Okay, and by the way, who do stuff and actually get stuff done and working. So don't make fun of them. Don't ever make fun of those people. So how would a person handle that if you hadn't taken 364? Well, it'd be 263. You'd look at it and you'd say, well, I know how to minimize that. That's no problem. That's that, but without the lambda there. That's p inverse q. Something like that. And then you'd look at it and you go, yeah, but I mean, this is a problem. And so here's how a human being would do it. They'd do this. They calculate p inverse q. That's x. If that x is inside the unit box, they'd have the sense to say, I'm done. Okay? Otherwise, they'd say, ow, x7 is like way big. Ouch, that's no good. So I will add to this, I will regularize, and I'll put plus a number, some number times x7 squared. Everybody cool on that? So you're adding a penalty for making x7 big. Okay? And you'd look at this, and it would turn out x12 is also big, and you'd add something there. Okay? Now don't make fun of these people. I don't, you shouldn't, right? So then you'd solve it again. And now x7 would be smaller, but now x7 is too small. Now x7 is, x7 has turned out to be plus minus, is 0.8. And you go, ooh, sorry, my weight was too big. So you back off on x7, and now other things are coming up and over. And you adjust these weights until you get tired, and you announce that's good enough. Okay? So everybody, listen, don't laugh. This is exactly how engineering is done. Least squares with weight twiddling. And period. That's how it's done. And if you think your field, like if you're in some field like machine learning or something, you think, oh no, how unsophisticated. People in my field are much more sophisticated. This is false. All fields do this. This is the way it really works. In those little cubicles down in Santa Clara. This is the way it's done. You're doing imaging. You don't like it. Too smoothed out. You go back and you tweak a parameter and you do it again. So anyway, no shame. Okay, all right. So actually, if you think about what this method is, this is weight twiddling. That's what this says. It's weight twiddling. It says pick some regularization weights, because that's what these are. And then it says update the regularization weights this way in a very organized way. It just goes, you just update them this way. So this is, in fact, a weight twiddling. So an economist would call this a price update algorithm. And maybe an engineer might call it a weight twiddling algorithm. Now, they might even actually, probably there's people who have even invented this and didn't know didn't know it. But anyway, okay. Everybody see what I'm saying here? Okay. Let's see, let me ask a couple of questions about it, just for fun, because I've noticed that the 364A material only soaked in a bit. If P, not fully, if P is banded, how fast can you do this? If P is banded. Let's say it's got a bandwidth around K. N is the size of X. How fast can you do that? What is it? What is it? N squared K. That's your opening bid? And look, that's better than N cubed, right? If P is full, that's N cubed. That's a Cholesky factorization and a forward and backward substitution, right? Let's make P banded. And you said N squared K, that was your opening. Ooh, I like that even better. So NK squared, you're right, that's the answer. Okay, so just to make it, if you want me to, let me just make a point here. If this is full, you probably don't want to do this for more than a couple of thousand. 3,000, 4,000, you start getting swapping and stuff like that on something like that. You have a bunch of all your friends' machines with quad-core things, and you run MPI and all that stuff. Whatever, you can go up to 5,000, 10,000 or something like that. But things are getting pretty hairy, okay? And they're getting pretty serious at that point, right? If this thing is if P is block banded or something like that, it's got a bandwidth of 10, how big do you think I could go, for example, my laptop, and solve that? Remember, the limit would be 1,000. I could do 2,000. It's growing like the cube, so every time you double, it goes up by a factor of 10 or 8 or whatever, right? So what's a rough number? Well, put it this way. We wouldn't have to worry at all on my laptop about 1 million. So I want to make a point here that knowing all this stuff about structure and then recognizing the context of problems puts you in a very, very good position. By the way, where would banded structure come up in a least squares problem? Does it ever come up? Where? Structures that are so actually banded. What does banded mean? Banded means that xi only interacts with like xj for some bound on I minus j. So if you had a sort of a truss or some mechanical thing that went like this, and kind of bars never went too far from one to the other, that would be a perfect example. Let me give you some others. Control, dynamic system. So just control is one, because there it's time. And for example, if you have a linear dynamical system or something like that, the third state at time 12 it interacts, roughly, with states one step before and one after, but then that's banded. How about this? How about all of signal processing? There's a small example for you. All of signal processing works that way, more or less, right? Because there the band structure comes from time. Signal processing means that each x is dependent only on a few, there's a bounded memory or how much it matters. Now the whole problem is coupled, right? Okay, this is just for fun, but I'm going to use, these are good. It's good to go over this stuff because, okay, I just use that as an excuse to go over that. Okay, so here's a problem instance. Where I guess we have 50 dimensions, and I took a step of 0.1. I can ask a question here about this. In this case, it turns out G is actually differentiable. So if G is differentiable, that actually justifies theoretically using a fixed step size. Actually in practice as well, because if you have a differentiable function, if you apply a fixed step size, and the step size is small enough, then you will converge to the true solution. Okay? So this shows G of lambda. These are lower bounds on the optimal value, like that. They converge. And this is the upper bound found by finding a nearby feasible point. And then let me just ask you, I don't even know because I didn't look at the code this morning on how I did this, but why don't you guess it? How, at each step of this algorithm, here, when you calculate this thing, by the way, if this thing is inside the unit box, you quit and you're done. You're globally optimal. Because you're both primal and dual, end of story, zero duality gap, everything's done. So at each step, at least one of these at least one component of this pops outside the unit box. Please give me some guesses. Give me just a heuristic for taking an x and producing from it something that's feasible for this problem. Simple. What would you do?
If the coordinate is bigger than 1, you make it 1. If it's less than -1, you make it -1.
There you go. So you just project. So in this case, it's too easy to calculate the projection. You just calculate the projection. And so, in fact, this thing here, I'm sure that's what this is, but x tilde is simply the projection of xk onto the unit box. So that's what that is. Okay. Okay, so that's that. Well, we're going to come back and see a lot more about projected subgradient methods applied to the dual later in the class. Okay, so let's look at a more general case. That's going to be subgradient method for constrained optimization. So here, instead of describing the constraints as just a constraint set, we'll write it out explicitly as some convex inequalities. So this goes like this. Here's the update. I mean, it's really dumb. I'll show you what it is. You simply do a subgradient step. And here's what you do. If the point is feasible, you do an objective subgradient step. If it's not feasible, then you find any violated constraint and use a subgradient of that. Okay? This makes sense? So it's really quite strange. In fact, what's kind of wild about it is that it actually works. So, I mean, you realize how myopic this is, right? It's very, very silly. It basically goes, so the algorithm goes like this. You're given x, and you start walking through the list of constraints. So you evaluate f1, f2, f3. If those are less than or equal to 0, you go to the next one. The first one, I mean, just that's a valid method. The first time you hit a violated constraint, so that j is positive, fj, you simply call fj.getSubgrad or something like that to generate a g, and you take a step in that direction. Does that reduce fj? No. Subgradient method is not a descent method. There's no reason. So basically, you go down, you find the 14th inequality is violated, you take a subgradient step, and that could and often does make the violation of the 14th inequality worse. Everybody I mean, the whole thing is like, these algorithms are just highly implausible. I mean, they're the kind of things where you need the proof because the algorithms themselves are so ludicrous, right? Okay. Now here we have to change a few things. FK best is the best objective value we have over all the points that are feasible. And this can actually be plus infinity if you haven't found any feasible points yet. So, that's that right? Yes. So FK best is initialized at plus infinity. Okay. So the convergence is basically the same. I won't go into the details. It just works. I mean, that's the power of these kind of very slow, very crude methods. In fact, that's going to come up in our next topic. What you can say about a subgradient methods is they're very unsophisticated, they're very slow, but actually one of the things you get in return for that is that they are very rugged. In fact, in the next lecture, which we'll get to very soon, you'll see exactly how rugged they are. It kind of makes sense, but anyway. So there it is. That's a typical result. And I think the proof of this is in the notes. You can look at it. But let's just do an inequality form LP. So let's minimize C transpose X subject to AX less than B. It's a problem with 20 variables and 200 inequalities. Let's see. The optimal value for that instance turns out to be minus 3.4. We have 1 over k step size here. Oh, by the way, when we do the feasibility step, you can do a Polyak step size. Because if you're doing a step on Fj, which is a violated inequality, what you're interested in is Fj equals 0. You are specifically interested in that, so your step size can be the Polyak step size. And this would be an example of sort of the convergence, F minus F star. I guess if F star is minus 3.4, then, well, look, this is not bad, right? I mean, this is, I don't know. Let's see. Let's find out where 10% is. 2, 3. There's 10%. Okay, so it took you about 500 steps to get 10% or something. So each step here costs what? What's the cost of a step here? Assuming dense, no structure. So what's the cost of a step in solving? Let's write that down. So we're gonna solve this problem. We're gonna minimize C transpose X subject to AX less than B. What's the cost of a subgradient of a subgradient method step here for this thing? You're exempted because you can't see it. So, is that true? You can't see it? No, you can't. You can't see it, right? Or you can see the constraints. That's actually the only important part. Okay. What's the cost? How do you do it? What's the method? If you're going to write it in MATLAB, how long would it be? For that matter, it's just as easy to write it in LAPACK, but let's write it in MATLAB. How long would it? What would it be? How do you implement this method here? Not this one, but by the way, of course, all the source code for this is online. But here's a method, right? So what's the method? Somebody tell me the method. Homework 3, Bull. You'll be doing this shortly enough. So what would be that? Well, okay. Here's a lazy way. You just evaluate AX and you compare to B. Okay? If AX is less than or equal to B, what's your update on X? It's X minus equals C, alpha C, right? Otherwise, if AX is not less than or equal to B, you find for example, you might as well find the maximum violated one, it doesn't matter. That's the point. You can take any violated one. But if you evaluate all of them, and that's just from laziness, you evaluate all of them, then what's the cost actually of evaluating this? I mean, there's your cost right there, just multiplying AX. What's that? Are you saying MN? Thank you. Good. Okay, MN. So, it's irritating. No, but I know you should. The thing is, you should know these things. These should not be abstract parts from 3 days of 364A. You should just know these things. You should know what the numbers are on modern processors and things like that. Just for fun, everybody should. After a while, then we quit, and then you go back, and it's just AX and stuff like that. So the cost here is MN per step. And so what that says. Whereas, how about what's the cost on an interior point method on this guy? Where's our What's our cost on it? What's an interior point step? In fact, what's the interior point method complexity, period, end of story on this guy? Just min C transpose X times AX less than B. At each step, you have to solve something that looks like A, D, A transpose, something or other, right? That's n. That's going to be n. I mean, let's exploit no story. That's n cubed. Okay, but forming A, D, A transpose. That's the joke on U. That's m n squared. M is bigger than n. That's the dominant term. So it's m n squared. Everybody? Okay. How many interior point steps does it take to solve this problem? What? Thank you, 20. So it's 20. So what's the overall complexity of solving this problem? mn squared. And remember what that is. It follows my mnemonic. It's the big dimension times the little dimension squared. This assumes you know what you're doing. If you do it the wrong way, it's the big dimension squared times the small dimension. So always ask yourself that. Okay, so it's mn squared versus mn. So basically, a subgradient step costs a factor of n more. N is 20. I mean, it doesn't, is 20. Is that right? Okay, so that says here, you really should divide these by 20. And so that's, you said 20 steps. So this is 25. You would actually have solved the problem here. You've solved it to about 10% accuracy with this subgradient type method here, roughly 10%, maybe a little bit better. But in an interior point method, in this amount of effort, roughly, in this amount of effort, you'd have the accuracy to 10 to the minus 10. Okay. So. Everything cool? Okay. All right. Let's see if I can. Oop. Is that going to work? That worked. I don't know what I've done, but okay. Let's see. Okay, so our next topic is the stochastic subgradient method, and we're going to get to some of the first things we can actually do with subgradient type methods that don't really have an analog in interior point methods. So we're now, so far they're just cool because they're 3 lines. The proof of convergence is 4 lines, and so on. We're going to see there's some very cool things about subgradient methods later, but now we're going to see something that's actually like different and isn't 364A compatible. So we're going to do stochastic subgradient method. And let me just give you the rough background on it. The rough background on it is that these methods, these subgradient methods, they're slow, but they're completely robust. I mean, they don't break down. They're 3 lines of code. 1 really, 2, something like that. They're 1 or 2 lines of code. They're very slow, and boy, are they robust. They just cannot be messed up. And we're going to see a very specific example of that. In fact, what's going to turn out that you can add noise, not small noise, to the subgradient calculator. Okay. Everyone would guess. And look, if you're doing stuff in double precision floating points, you're always adding noise every time you call anything. In an interior point method, you say, get me the gradient. That comes back with noise. I guess in EE, we would say with something like 200 decibel signal-to-noise ratio, because that's what a IEEE floating point gives you or something. But it comes back already with noise, but it's on the order of like 1e minus 8 or 1e minus 10 times the size of the thing you're calculating, right? That's standard. It's going to turn out here. So no one would be surprised if a barrier method continued to work if there was noise that was in the 6th figure of your gradient calculation. That would hardly be surprising. 5th figure. Again, 4th figure, you could start imagining having some trouble now. The subgradient methods, they work this way. Here's how stupid and robust they are. Not only you can actually have a signal-to-noise ratio that's quite negative in dB. So in other words, you can have basically a subgradient where the signal-to-noise ratio is 1. In other words, that means basically when the person says the subgradient is like that direction, the true subgradient could actually be back there. It's just sort of if you ask them 50 times or 100 times or something, they should be kind of average out vaguely to the right direction. Everybody got this? So, which is cool. actually. It has lots of applications. Okay, so let me define a noisy, unbiased subgradient. So here's what it is. So I have a fixed, this is a deterministic point, x, and I have a noisy, unbiased subgradient for f at x is this. It is a vector, a random vector g tilde that satisfies this, that it's on average, its expected value is a subgradient. Okay? Now, by the way, this means, of course, that for any particular g tilde, this inequality is false. I mean, obviously, need not hold, right? So, however, on average, so basically think of your f dot get subgrad as being it's not deterministic. That when you call it, it gives you different g's. But if you call it a zillion times an average, that would give you something close to the mean. That's close to a subgradient. Everybody got it? Okay. So we'll see lots of practical examples where you get things like that. Okay. Another way to say it is this, is that what comes back is a true subgradient plus a noise, which is zero mean. That's a stochastic subgradient. Now, this error here, it can represent all sorts of things. It can be, first of all, it can just be computation error. That just basically when you calculate subgradient, you're sloppy, or you do it in fixed point, or I don't know, what it's anything like that. But it could also be measurement noise. We're going to see it's going to be Monte Carlo sampling error. So if, in fact, the function itself is an expected value of something, and you estimate an expected value by Monte Carlo, then you write, it's unbiased. I mean, if it's unbiased estimator, you write it down as, if it's an expected value, then the average is the right thing. You get, it's unbiased, and then V is actually the difference between, it's a random variable, and it's the difference between what you actually get, it's your Monte Carlo sampling error. I'll just leave it that way. Okay. Now, if X is also random, then you say that G tilde is a noisy unbiased subgradient if the following is true. For all Z, this holds almost surely. Now, this is the conditional expectation of G tilde. That's the noisy subgradient conditioned on X. Now, that's a random variable. So this right-hand side is a random variable. That's not a random variable. And it's also a random variable because X here is a random variable. So the whole thing on the right is a random variable. And if this inequality holds almost surely, then you call it a noisy, unbiased subgradient. So that's what it is. Okay. And that's the same as saying the following. It says that the conditional expectation of G tilde given X is a subgradient of F at X almost surely. So that's what it means, right? If for the conditional one, I mean, if X is not random, it's like that. I don't need the condition on X, and I can erase that. So let's see. I don't know what this means. Well, anyway, that's what it means. This is a random vector. That's a random vector, and the idea is that, and that's actually a random set. And so it basically says that inequality holds almost surely. Okay. So. Okay. Now here's the stochastic subgradient method. Ready? It's this. Here. So, in other words, it's the subgradient method. So it says you got a noisy subgradient. I'll just use it. I'll just use it. No, nothing else. So you basically update like that, and that's it. Now I want to point something out. This is now a stochastic process, right? Because even if x0, if your initial x was deterministic, then g0 is already a random variable, and therefore x1 is a random variable, the first update, because it depends on g0. And so this is now a stochastic process, this thing, okay? So we now have a stochastic process, which is the stochastic subgradient, the trajectory of the stochastic subgradient method. And here you just have any noisy unbiased subgradient. And then we'll take, that's the step size, the same as always. And then fk best is going to be the min of these things. By the way, that's a random variable now, right? Because that's now a stochastic process here. So that's a stochastic process, and that's a random variable, is fk best. Okay? So, okay. So here's some assumptions. The first is we'll assume that the problem is bounded below. These are much stronger than you need, but that's good enough. We'll make this global Lipschitz condition here. More sophisticated methods, you can relax these, but that's okay. And we'll take the expected value of x1 minus x star less than this. Now, x1, by the way, could be just a fixed number, in which case you don't even need this expected value. It's the same as before. Now we're going to have the step sizes, they're going to be square summable, but not summable. So, for example, 1 over k would do the trick. Okay, so you're going to take an L2, but not L1, little L2, but not little L1 sequence of step. 1 over k is fine. Okay. Here are the convergence results. Okay, I'll summarize this one. It works. This says that that it converges in probability. And in fact, you have almost sure convergence. We're not going to prove this one, although it's not that hard to do. This one. We will show. Actually, we'll show this. This will follow immediately from that. Since these are fk minus fk is bigger than f star, so that'll follow immediately. But that's the picture. So before we go on and look at all this, I just want to point out how ridiculous this is. So okay, so first of all, the subgradient method by itself, I think, is ridiculous enough. It basically says you want to minimize, like you want to do a minimax problem. It says no problem. At each step, go around and find out which of the functions is the maximum. If there's more than one, arbitrarily break ties. Return a, let's say, gradient of that one, and take a step in that direction. That's totally stupid, because if you're doing minimax, the whole point is when you finish, a lot of these things are going to be tied. And the whole point is you don't want to just step greedily to improve one of these functions when you have a bunch of them. It just says do it, and the 1 over k step size are going to take care of everything. What's wild about this is that method, though, is so robust that in fact your get subgradient algorithm can be so bad that it can actually, as long as on average it's returning valid subgradients, it's going to work. So signal to noise ratio could be minus 20 decibels. You could be getting whenever you get a subgradient, you could be adding to that a noise 10 times bigger than the actual subgradient. Everybody see this? The whole thing is completely ridiculous. Now, will the convergence be fast? No. It can't. I mean, it can hardly be fast if someone's only giving you a subgradient, which is kind of a crappy directions anyway for where to go. But now, if they give you a subgradient with a negative 20 decibel signal-to-noise ratio, in other words, basically it says that you can't even trust the subgradient within a factor of 10. You'd have to you'd actually ask for subgradient directions like 10 or 100. You'd call it 100 times and average the answers. And that's the only time you could start getting some moderately sensible direction to go in. Everybody see what I'm saying here? The whole thing's quite ridiculous. Okay. And here's the summary is, it just works. It just works. So these are kind of cool because they're just, wow. It's also, this is known and used in a lot of different things, signal processing and all sorts of other areas. Well, actually, there's a big resurgence of interest in this right now in what people call online algorithms. And that's being done by people in CS and machine learning and stuff like that. Okay, so let's look at the convergence proof. It's tricky. You won't get the subtleties here, but you can look at the notes too. It's not simple. I don't know. I got very deeply confused, and you have to go over it very carefully. So that it's subtle you won't get from this, but let's look at it. So it goes like this. We're going to look at the conditional expectation of the distance to an optimal point given xk. The next distance here. Now, this thing is nothing but that, so we just plug that in. And we do the same thing we did with the subgradient method. We split it out. We take this minus this. That's one term, and we get this term. Now, that, and this is conditioned on xk. So xk conditioned on xk is xk. So this loses the conditional expectation condition on xk. That's a random variable, of course, but you lose the conditional expectation. Okay, well, it's the same. And you get this. You get 2 alpha times the conditional expectation of, now it's the cross product of this minus this and that term. And that's this thing, conditioned on xk. And the last term is you get alpha squared times the conditional expectation of the subgradient squared given xk. And we're just going to leave that term and leave it alone. Now, this term in here, we're going to break up into 2 things. We're going to write it this way. It's I can take here, the x star is a constant, and so conditioned on xk, that's just x star. And then this term, g tilde k transpose x star, that's linear in this, so conditional expectation commutes with linear operators, so that comes around, and you get this thing. Now, this thing here, the definition of being a noisy stochastic subgradient, or a stochastic subgradient if you like, is that this thing here should be, I guess it's bigger than or equal to, or whatever the correct inequality is, this, to make this thing true. Okay? So that's how that works. And so you end up with this. Now, if you go back and look at the proof of the gradient method, subgradient method, it looks the same, except there's not the conditional expectations around. And there's a few extra lines in here because of the conditional expectations. Okay, so let's look at this. And this inequality here is going to hold almost surely. Everything here is a random variable. That's a random variable. This entire thing over here is a random variable. Okay, so this inequality holds almost sure. This thing is less than that. And now what you can do is the following. We can actually telescope. I mean, we can actually now telescope stuff, the same as before. If we take expectation of this now, then the expectation of this is just the same as the expected value of that. That's a number, and that's less than the expected value of that, minus than the expected value of that. Expected value of that just drops the conditional part there. And so here's what you get. You end up, if you take expectation of left and right-hand sides of the inequality above, which was an inequality that holds almost surely, you get this. The expected distance to the optimal point in the next step is less than the current distance to the next point minus 2 alpha k times the expected value of your suboptimality here, plus alpha squared times the expected value of the subgradient squared. Now, this thing will replace with just the number g squared here. And we'll apply this recursively, and you end up with this, that the expected value of xk plus 1 squared minus x star is less than the expected value of x1 minus x squared. This is going to be less than r squared here, this thing. That's our assumption. And then again, we get the good guy and the bad guy. That's bad. This is good because this thing is always bigger than that by definition. So whatever this is here, it's a number. Whatever this number is, it's non-negative here. I guess it's positive or something like that. So that's a positive number. There's a negative sign here, so this is on our side. It's actually making this distance smaller. And the nice part about that is that goes in alpha. This goes in alpha squared. And so the bad guy, at least for small enough alpha, is going to lose. And then you just simply turn this around and you get the following. You get the minimum of I equals 1 to k of the expected value of your suboptimality is less than or equal to r squared plus g squared and norm alpha squared over. It's the same thing as before. Right? So it's exactly what we had before. Okay. Except now it's the minimum of the expected value of the suboptimality. That's actually a random variable here. So that's the difference. Okay. Now, this tells us immediately that the expected value of this sequence actually converges. The min of these expected values converges to f star. That's what it tells you. Actually, I believe that the fact is you don't even need the min here. This converges. That's a stronger result, but we don't need it. We'll get to that. Now we're going to apply Jensen's inequality. So Jensen's inequality says the following. I'm going to commute expectation and min. Min is a concave function. So what that says is the following. Here I have the expectation of the min, and here I have the min of the expectation. And I guess the inequality goes this way. But this thing here is a random variable, and it's the random variable fk best. And so expected value of fk best is less than or equal to this. This thing goes to 0, so we're done. Okay? By the way, I never remember which way Jensen's inequality goes. So I'm not ashamed to admit it. So I usually have to go to a quiet place or draw a little picture with this and some lines. Because every time you do it, it's something different. It's either a concave or whatever. And it's important which way it goes. So I just go somewhere quiet, I draw a picture, and then come back and see how it goes. So I'm trusting myself that this is correct. I think it is. Okay, but once you know this, you're done. But this is, now you're done with, you can get convergence of probability very easily because these random variables are non-negative. So these are non-negative. So the probability that a positive random variable is bigger than epsilon is less than that. And we already know the numerator goes to 0. So for any epsilon, this goes to 0. And so you get convergence in probability. Okay? So, by the way, this is not simple stuff. I mean, it's not complicated. It did fit on 2 slides with giant font size. But trust me, it's not totally straightforward. And I think the notes has this in more detail. So, okay, but let's do an example. So here's an example: piecewise linear minimization. And now here's what we're going to do. We're going to use stochastic subgradient method, except that the way how do you get a subgradient of this thing? What's a subgradient? How do you get a subgradient of this? What do? Yeah, you evaluate you have to evaluate all of these, okay? Because otherwise you don't know what the maximum is. You evaluate all of them, find the maximum value, then go back and find one of them that had maximum value. Break ties arbitrarily. It could be the last one that had maximum value, and then you return AI. So here's what we're going to do. We will actually artificially we'll just add zero mean random noise to it. We'll just add noise. So we'll add noise in our f.getSubgrad method. That's what we're going to do. And here's just a problem instance with 20 variables. M equals 100. You have 100 terms. The same as before. F star is about 1.1. It's the same example. 1 over k step size, and the noises are have about they're about 25% of the size of the subgradients, because the average size of the subgradients is around 4. And the noise is the average size is, well, let's see. Each of these is about 0.7 or something like that, or whatever. So that's about 25%, something like that. Okay. And here's what happens. If you have here's the noise-free case, so you get this. And so indeed, so I should say what this means is you're getting the subgradient at about how many bits of accuracy are you getting in your subgradient? Here. When you call subgradient, how many bits of accuracy are you getting here? I mean, if your noise is on the order of a quarter, I just want a rough number. How many bits of accuracy are we talking here? This is 20. What would you just roughly, if you had to say signal noise ratio 1 to 4? No, 4 to 1. Roughly how many bits? It's not a hard question. I mean, it's not a complicated question, so people are probably way over computing or something like that. It's 2, roughly. What? You said 2.5? You believe 2? No. 2, I said. You think it's 12? I think it's 2, right? It basically means, if I tell you if I tell you the subgradient is this, you could be off by as much as 25%. That's kind of rough. I mean, this is just all hand waving, but that roughly means it's about 2 bits of accuracy. That's not a whole lot of accuracy, right? So that's the point. These are really quite crude. And you can see what happens is actually interesting. Here's one realization, and here's another. Actually, in this one, we're really lucky. The errors in the subgradient were such that they didn't mess us up very much. And that's another one where it did, although it can't be stopped. Now, these are big numbers here. That's about that's 10. The interesting thing is, is to get to 10% accuracy, it probably multiplied the number of steps by 4 or something, all that. So the really cool part is that you would get, what would happen if the signal to noise ratio were inverted? Suppose the signal were 4 times as big as suppose when you got subgradient, we took this to be, I guess, whatever, that's 0.5 squared, 4, suppose the signal to noise ratio were reversed, and it was, the signal to noise ratio was 0.25, not 4. I mean, roughly, something like that. What do you think would happen here? Well, first of all, we know the theory says it's going to work. But think about how ridiculous that is, basically. You calculate like the worst G, that says go in that direction, and to that vector, you add a Gaussian, which is 4 times bigger. Which means basically, it would be very difficult to distinguish between your get subgrad method and just completely random, like, well, which way should I go? And you go like, oh, that way, and it's like, really? Can you verify that? And you go, that way. It's just totally random. You'd have to do that like 1,000 times and average them to even see slightly that there's some signal there. Everybody see what I'm saying? What would happen, of course, is that this would be, is that it would now mess it up much more. I mean, these would be like that. That's what would happen. So this shows you what happens is we do 100 realizations. You generate 100 stochastic processes, which is the stochastic subgradient method running forward in time. And this shows you the average here. And this shows you the standard deviation. That's a log scale, so that's why these things look weirdly asymmetric. So on a linear scale, this is plus minus one standard deviation. This is also plus minus 1 standard deviation, but it's on a log scale. But that's what it is. So, by the way, it's actually kind of interesting. These points down here correspond to cases where the noise was kind of bad. The noise accidentally pointed you in the right direction. And as a result, you did actually quite well. And of course, these are cases where the noise kind of was hurting you as much as possible. Make sense? So it's I guess the summary of this is that the subgradient method, you can make fun of it, it's very slow, and all that kind of stuff. But the wild part is actually any zero mean noise added to it doesn't hurt it. And we're not talking noise in the 5th digit. We're talking, if you like, noise in the minus 5th digit, if you want. So you can actually, which is quite ridiculous if you think about it. Don't try a Newton method when you're calculating your gradients or your Hessians with 25% noise. For that matter, don't try it if your signal to noise ratio is 1 to 4. So it's off the other way around. Okay. So these are empirical distributions of your suboptimality at 250, 1,000, and 5,000 steps here. And they look like this. And you could actually see, these would be the ones at the top of that plot, those error bars. And then these would be the ones at the bottom. But you can sort of see that the distribution is very slowly, going down like this, like that. So that's the picture. Let me ask one question about this problem. How would you deal with this in a 364A context? Suppose I told you you need to minimize a piecewise linear function. But unfortunately, the only method whose source code I won't let you look at, the only thing that calculates this thing only does it to 2 bits of accuracy. Or another way to say it is, every time you call it, you're going to get a subgradient plus a noise, which is as big as a quarter the size of the actual subgradient. How would you deal with that in 364A? We didn't really have a method to deal with this, but now just tell me, what would you do? What would you do?
You could call that function 10,000 times.
Right. Right. Okay. So 10,000. And Okay, good. 10,000 was a good choice of number, by the way. So you call that, so you'd call the number 10,000 times, and then you'd average those subgradients. And what would be the, roughly how much error is in the one that's 10,000 times? Oh, come on. I was hoping for you to say, I was going to go down by square root of 10,000. That's why I was complimenting your choice of 10,000, because it had a nice square root as 100. So instead of being an error being 25%, it would be 0.25%. So, that might be enough to actually run a gradient method. It probably would work okay. So what would happen is at the end game, it would kind of start being erratic or something, but you get a pretty good answer pretty quickly. Okay. By the way, if you evaluate it 10,000 times, I should point something out. This is beating you, so it's not clear. So it's not clear anyway. But you're right. That's what you do. Okay. So this is actually maybe a good time to talk about stochastic programming. Actually, at some point I want to make a whole lecture on this because it's quite cool. Everybody should know about it. And it's this. In stochastic programming, you're going to explicitly take into account some uncertainty in the objective and the constraints. So that's stochastic. There's something called robust programming where you have uncertainty, but you model it in a different way and you look for worst case type things. But for stochastic, that's a very common, very old method, something like that. I mean, I should mention, it's kind of obvious that this comes up in practice all the time, right? So anytime anybody's solving an optimization problem, you just point to any data oh, by the way, I should mention this. If you were not at the problem session yesterday, you should find someone who was and ask them what I said. I don't remember what I said, but some of it is probably useful or whatever. So you take any problem, a linear program, and what you do is then you ask the person solving the linear program, you point to a coefficient, not a zero, because zeros are often really zero. Also ones, those are also not good choices, because one is often really one. But you point to any other coefficient that's not 0 or 1, and you ask them, what is that coefficient? And that coefficient has a provenance. It traces back to various things. If it's a robot, it traces back to a length and a motor constant and a moment of inertia or whatever. If it's a finance problem, it traces back to a mean return, a correlation between two asset returns, or who knows what. If it's signal processing, it goes back to a noise or a signal statistics parameter, for example. Everybody see what I'm saying? And then you look at them and you say, and you really know that thing to 8 significant figures? And now if they're honest, they'll say, of course not. And the truth is they really only know it to depends on the application, but it could be 3 significant figures in a really lucky case. Could be 4, could be 2, could be 1. And actually, if you get some economists in the right after a couple of glasses of wine, they'll look up and say, if we get the sign right, we're happy. Anyway. But until then, they won't admit that. Right? So, okay. So the point of all this is it's kind of obvious that if you're solving a problem, the data, if you point to a data value and propagate, it has a provenance and it traces back to things that probably you don't know better than like a percent. It depends on the application, but let's just say a percent. By the way, if you don't know any of the data, if you barely know the sign of the data, my recommendation with respect to optimization, my comment is real simple. It's why bother, right? So if it's really true that you don't know anything about the model, then you might as well just do it by intuition and do your investments or your whatever you want. Just do it by intuition. Just guess. Because if you don't know anything, using smart methods is not going to really help. So typically, like 1 significant figure, maybe 2, maybe 3 or something like that, and so on. And then, by the way, all the stuff from this whole year, now it starts paying off a lot. And there are weird sick cases where you know things to high accuracy. GPS is one, for example, where, you point to some number and they go, you really know that to 14 like decimal place, and they're like, yes. And you're like that. I mean, I find it weird, but anyway. So normal stuff is accurate between 1, 0 is like why bother for this, 1, 2, 3, 5, 6. I guess in some signal processing things, you can talk about 15 bits or something like that, 20, but then rarely more than that. Okay. All right. So there's a lot of ways of dealing with uncertainty. I mean, the main one is to do a posterior analysis. That's very common. So let me tell you people know what a posterior analysis is? All right, so posterior analysis goes like this. You're making it doesn't really matter. You're making I don't care. Let's make a decode. Let's make you're making a control system for a robot. I don't care. Something like that, right? So you sit around and you work out a control system, and when you work out the control system, you can trace your data back, and there is a stiffness in there, and there's a length of the link to, and there's an angle, and there's all this stuff. There's a motor constant. There's all sorts of junk in there, and they have nut values. And you have a robot controller, and you get some controller, and now before you implement it on the robot, I mean, that'd be the simplest way, but the first thing you do is you do something called a posterior analysis. So posterior analysis goes like this. You take the controller, or the optimization variable, whatever it is, designed on the basis of one particular value, like a nominal value of all those parameters. You take that, and you re-simulate it with those values, multiple instances of those values, generated according to plausible distributions. Everybody see what I'm saying? So, and by the way, if you don't do this, then it's called it's called stupid, actually. This is just absolutely standard engineering practice. Unfortunately, it's done in, I'd say, about 15% of cases. Don't ask me why. So, in other words, you design a robot controller, you optimize a portfolio, anything you do machine learning. Actually, in statistics, this is absolutely ingrained in people from when they're small children. In statistics, you do this. It's the validation set or something like that. So here's what you do. You design that controller on the basis of a length and a motor constant, which is this. That motor constant depends on temperature and all sorts of other crap. You ask somebody who knows about motors, and you say, how well do you know that motor constant? And they'd say, I don't know, 5 plus minus 5%, something like that. You go to someone in finance, and you say, you really believe that these two assets are 57.366 percent correlated? And they go, no, but it's between 20 and 30% correlated, maybe, right? You go, thank you. Then what you do is you take that portfolio allocation and you simulate the risk and return with lots of new data which are randomly and plausibly chosen. Everybody see what I'm saying? You change the motor constant plus 5%, minus 5%. Moment of inertia, change it. The load you're picking up, you don't know that within more than a few percent. You vary those. And then you simply simulate, and you see what happens. If you get nice, tight curves, so in other words, that means that your design is relatively insensitive, everything's cool, and now you download it to the actual real-time controller. Or you drop it over to the real trading engine, or whatever you want to do, right? So that's how that works. So that's a standard method. That's posterior analysis. Stochastic optimization is actually going to be dealing with the uncertainty directly and explicitly. And I guess we'll continue this next time. Let me repeat for those who came in late, grovel, I'm not sure what the word is, at 12:50 to 2:05 today here, we're having the world's first, I believe, I haven't been notified from SCPD that it's not true, the world's first tape behind. We'll have a dramatic reenactment of lecture 1. So come if you can.